x-axis.
Negative x-axis and along the positive direction of y-axis. Okay. Then second, let's see second operations.
Second operation means that's one only.
Okay. Now let's see few more examples. The computations of determinant using matrices, etc. The first example is 1a square. You see on the screen 1b square, 1c square. Now this matrix A, if you take its determinant, then instead of we have two vertical bars, and now you see on the screen the first two rows. Now 1a square, 1b square. Now if you take A equal to b, then to both the rows R1 and R2 are identical, so value of the determinant is 0, and so by factor theorem you can see A minus B is a factor. Same way, if you take B equal to C, that is second and third, then row becomes identical, and therefore again determinant is 0, so B minus C is again a factor. And same way, if you take A equal to C, again determinant is 0, so A minus C is a factor. And so determinant A is K times A minus B, B minus C, C minus A, and comparing the equal power, we see that K equal to 1, so here determinant is simply determinant is A minus B, B minus C, C minus A. Not only that, instead of this, you can have the elementary operations. Now, if you have from third row, you subtract A times second row, and from second row minus A times first row. In that case, again you have from second and third row B minus A, your A minus B, negative of that, B minus A common from second row, and from third row you have C minus A common. So when you take those things out, the resultant matrix you get, resultant determinant form, you get 1 0 0, 1 1 B and 1 1 C, and when you expand this, you get simply C minus B, and taking care of the changes by changing sign, you get again the same thing, A minus B, B minus C, C minus A. So again determinant you get A minus B. Or a third way is you just see the second, just on the screen, second row A, B, C. Second row A, B, C. You multiply the second row by A and then subtract it from third row, and same way first row you multiply by A and subtract from second row, and again do the same operations, then you get again the same result, determinant A equal to A minus B, B minus C, C minus A. If A, B, C are distinct, in that case this determinant is not 0. In that case you have A invertible, that is A is non-singular and determinant is not 0, and same way you can take another matrix on the screen. You can see on the screen we have first row A square 1 plus A cube, B square 1 plus B cube, C square 1 plus C cube equal to 0. Value of the determinant is given, and this 1A square vector, 1B square, 1C square, they are linearly independent or they are not collinear. Now we are interested in finding what is the value of A, B, C. Now we use the previous result, and this determinant can be expressed as 1 A, B, C, A square, B square, C square. Now we take only first terms of the third column. So 1, 1, 1 and plus we are using the properties of determinant, and in the second we got A, B, C, A square, B square, C square, first two columns as they are, and third column A cube, B cube, C cube. Now from the second we can take out from first row A, from second B and third C. So you got A, B, C, and then you got what remains is 1, 1, 1,
ABC.
A, B, C,
A square, B square.
A square, B square, C square. And we got in the first, so this matrix you can take out, and what remains is 1, 1, 1, A, B, C, A square, B square, C square, common we take, then we got A, B, C. So in that case, previous result, when A is not equal to B, B not equal to C, means A, B, C are distinct, then this determinant A is not 0, because A minus B, B minus C, C minus A is not 0, and because we are in R, real number system, so in that case the second factor, that is 1 plus ABC must be 0, and that gives the product ABC equal to minus 1. You can use the same thing. Let's see few more problems. Determinant functions is neither additive in the sense that given any functions, if you take f a plus b, f a plus f b, this property is not true in the determinant. So it is not additive and also not homogeneous. That is f of alpha a equal to alpha of f a. So this property are no more true. So it is neither additive nor homogeneous. As for example, you take one example, just let us illustrate by some example. A is this one and B is minus 1, 1, minus 1, minus 1. Now if you see this A and B, then determinant A, 1 minus 1 plus 1 minus minus 1, so 1 plus 1 2, and that is same as determinant B, 1 plus 1 B. So determinant A is not 0, determinant B is not 0, and if you take determinant A plus B, then when you add A plus B you take, then you get everything is 0. 1 minus 1, minus 1 plus 1, 1 minus 1, and so determinant A plus B is 0, whereas determinant A plus determinant of B is 4. So 0 is not equal to 4. So this property of additivity is not true in case of determinant. And same way, if you take determinant of alpha A, this will not be equal to alpha f A. This property also not true, because that is the basic difference between matrices and determinant. In the matrix, if you multiply by some constant, some non-zero constant, all the entries of the matrix are multiplied by that constant, whereas in the determinant you take any row, if you multiply any row by that constant can be taken out, or anything outside you can bring inside, and same way for columns. So here when you take, so suppose you take a matrix A, and say let us take 1 2 0 1, simple 1 2 1 2 0 4, and you multiply by 4, or let us take 4, then the matrix becomes 4, then 8, then 16. So this is the matrix. When you take its determinant, here 2 by 2, same way n by n you can take. So here, in that case, from every row you can take 4 out, so it is 4 square, and again you get 8. The remaining is 8. So here 16 times and not 4 times. And suppose you have n by n matrix. If you have n by n matrix, then determinant of alpha A, where A is n by n matrix, in that case, alpha raised to n comes out. And so when n is greater than 1, you will never have the homogeneous property. Another thing is, though it is not additive and homogeneous, it is multiplicative. The determinant function is multiplicative. That's the beauty, and that property is used many places, not only in science but in all the stream of knowledge, and that is determinant of A is determinant A into determinant of B. So the multiplicative property is there. So determinant function is multiplicative. There are other problems. I just give you as an exercise because we don't have the time. But using the properties, just one problem, let's call lambda 1 is this determinant x, b, a, x, b, a, x, and delta 2 is x, b, a, x. Now, let us interplay the determinant property, equations, system of equations, and derivative. Let us find derivative of delta 1. Then what happens? When you find the derivative of delta 1, what it has to do with delta 2. Okay, here 3 by 3 matrix, it's determinant, here 2 by 2, and you see that d dx of delta 1 is nothing but 3 times delta 2. So that's also a beautiful property one can see. Another problem, that's a nice problem, and you can discuss this. Let us take the matrix of order n. First row is 2, minus 1, 0, 0, 0, and minus 1, 2, minus 1, 0, 0, everything, and then 0, minus 1, 2, minus 1, and so on. This way it continues, 0, 0, 0, and minus 1, 2, minus 1, 2, minus 1. Now, find the value of the determinant an. Find the value of determinant an. Here also, one can use recursion formula. You can use that equations and get the solutions very easily. Value of the determinant. So, thank you very much. Any questions? Okay, thank you.